So welcome. Today we're going to see a presentation from John Paul Takacs, who's completing his mathematics major, and he's going to speak to us about modeling tsunami wave propagation. Take it away, John Paul.
Yeah, so as Boardman said, my name is John Paul Takacs, and for my capstone, I wanted to look at modeling tsunami wave propagation, and in particular, looking at how that wave develops over a sea of non-constant depth. So to start with, we can look at the basic 1D wave equation. So in the first half of the semester or the year, we looked a little bit at this derivation and understanding it, but for now, I'm just gonna stick it up here and then explain what it is. So in this case, we have some function u, and we're gonna say, u is describing kind of position. And in this case, it would be of a string. So we'd pull a string to a displacement, we'd see kind of a ripple effect, and this equation models that. And so we have our function u, and we take the second derivative with respect to time on the left, is going to equal a constant squared times the second derivative with respect to location x. And a general solution of this would be u sub xt equals a sine of theta. And in this case, a is basically saying, that's our wave's amplitude. Now, this would be for a string. This would give us sort of this ripple effect on a string, but that's not what we're looking for. A tsunami wave has this kind of shift. It has this motion along the x-axis. So what we need to do is we need to incorporate a phase shift. So what we've done is we've said, theta is going to equal 2 pi, and we're using 2 pi because sine is going to be periodic of 2 pi. And we're going to multiply that by x over lambda minus t over capital T. And the idea here is that lambda is going to be our wave's length. So distance from trough to trough or crest to crest. T is going to be the period, or the amount of time it takes for that wave to move kind of one unit, or one wavelength, if you want to think of it that way. So solving for wave speed. Now this looks a little bit complicated up top, but it's really not. All I've done is I've said, 2 pi over lambda, we're just going to call that k. 2 pi over the period, we're just going to call that omega. And what I've done is I've taken the two derivatives respectively. So we have the second derivative with respect to t over on the left, second derivative with respect to x over on the right, and I've replaced a with h over 2. And for me, it was easier to think of that. H is the wave's total height, so from the trough up to the crest. So when we take those respective derivatives, we're left with what you see up on the top, and then we can algebraically solve that for c. And this kind of shows, yes, this does work. This is a solution. We're left with a constant. But what is c? Well, in this case, c is the wave's length over the wave's period. That's kind of intuitive. We're saying the wave's speed in this case, as c represents the phase speed of that wave, is just the distance you're going over the time it takes you to get there, which would be velocity. So that's pretty intuitive, but it's nice to see it works. So our modified wave equation. Now, what we looked at before is assuming c is a constant. We're saying, there's a constant wave speed, but when we incorporate a non-constant depth, that wave speed is going to change, as the wave's phase speed is kind of dependent on what the water depth is, things like gravity, viscosity, and all of that. So we need to adapt our equation a little bit. And this top one, I did not derive this personally. This came from a lot of my sources, but it sort of makes that adjustment. And then we have wave speed. And when we start to consider water depth, obviously that wave speed is changing. So we get this square root, which is gravity. G is representing gravity times the wavelength over 2 pi, hyperbolic tangent of 2 pi h over lambda, and h is representing our water's depth. Now, there's some interesting assumptions we can make when we look at a tsunami wave, and some simplifications we can work with. So a tsunami wave is going to act like a shallow water wave. And the reason being, it has a very long wavelength. It's, you can just think it's a big wave. So no matter how deep the water is, within reason, it's going to act like a shallow water wave. It's going to meet that seafloor friction. So we're going to take a limit of that, and we can sort of do it intuitively. As our water depth starts getting shallower, our wavelength is going to compress a little bit, so lambda is going to decrease a little bit, but not as much as h. And essentially, we'll get this limit of c of x being the square root of gravity times water depth, or c of x equals square root of gravity times h of x. And h of x is a function describing water depth with respect to location. So one of the things we see here is, this is going to be very hard to find a continuous solution for. I worked for quite a while trying to describe the amplitude using things like oscillatory motion, Hooke's law, and it really got a little bit complicated. So we turned to numerical methods. So what we have above is we have just the limit definition of the first derivative. And what we can do is we can take the Taylor series expansion of that term, and we can find sort of an approximation using it. So the way we're going to do that is we're going to take the Taylor series expansion for f of x naught plus a little bit. So we have some x naught, we know the value there. We want to approximate what is it the next step over. So we're going to take the Taylor series expansion for f of x naught plus delta x. And that's what you see listed down here. And then we're going to take the Taylor series expansion for f of x naught minus a little bit. And the reason we're doing this is that, we could use an asymmetric difference method where we take the point we're at, the point we're going to, we can approximate the slope between those, and that's going to be the value of our derivative. But we can also say this is the point we're at in the middle. We're going to take a point to the right, we're going to take a point to the left, draw a secant line, and take that slope as being the value of our derivative. And that'll give us a much, much more accurate approximation. So we now have these Taylor series expansions for the point to the right and the point to the left. So where things start to get really interesting is where we subtract that second Taylor series expansion from the first. So we're taking the Taylor series expansion for f of x naught plus delta x, and then subtracting the Taylor series expansion for f of x naught minus delta x, which gives us what you see up above. If we divide both sides off by 2 delta x, we're kind of left with a bunch of stuff on the left, f prime of x naught, and a bunch of stuff. And what we're going to say is, this minus 2 delta x squared over 3 factorial and so on, those terms, they're really small. And in this case, they're alternating, but that doesn't really matter too much. The key thing is they're very, very small values. So we're going to say we're working with an approximation. Those terms don't really matter, so we're just going to cut them off. And we're going to say our symmetric difference approximation for the first derivative is what you see here on the bottom of the slide. But that's the first derivative. Our wave equation is going to be working with a second derivative. So in order to do that, we need to find an approximation for the second derivative. So to do that, we're going to add our two Taylor series expansions. And you'll see there's a few terms here that cancel out. But the idea is right there in the middle, you have f of x naught plus delta x plus f of x naught minus delta x minus 2 f of x naught over delta x squared. And that's equal to our second derivative plus a bunch of stuff. And sort of as we did before, we're saying that stuff kind of after the second derivative is really, really small terms. That doesn't really influence our approximation too much. So we're just going to cut those off. And we're going to say our approximation for the second derivative is what's on the bottom of the slide. So to recap a little bit, we're just going to review what we have. So we have a symmetric difference method approximation for the first and for the second derivatives. So now what we need to do is we need to apply these to our wave equation. So just bringing back our modified wave equation that we're working with, how do we apply that? Well, we're going to incorporate some new notation. And this is a bit of a conceptual jump, so I'll explain it the best I can. But we're going to say, little u is kind of our exact function. We're going to say big U is kind of an approximation of that function. So I'll explain what u sub n to the k is. So you can think of sort of a mesh, or you could think of a matrix. It might be easier with a matrix. But you have kind of rows and you have columns. And we can say we're going to go along the x-axis to the nth entry, and then we're going to go along the time to the kth entry, and we're going to have sort of a coordinate. So we can say at the n and k location, or indexed within our mesh, there's going to be a point. And that point is going to hold a value. That value is the height of the wave at those corresponding x and t values. So when we plug that in, and here we've just taken the respective derivatives and kind of distributed through our C, we're left with what you see on the bottom. And that's using these symmetric difference methods within our wave equation. So out of that, we get some interesting stuff. So let's just say C is constant. We're going to simplify things a little bit. Well, then our derivative of C is going to be C prime sub n, which is going to end up being 0. And that then means everything you see in red in the middle of the screen, that term's just going to go away. We're left with what's on the bottom. So that would be our symmetric difference method for our wave equation, which would just be our standard 1D wave equation. That brings us right back to the beginning, where C is a constant. And you'll notice that I do not have C squared here. The reason is, in this case, C is just a constant. And c squared is just going to be another constant. So why not just put in big C? For me, it was easier to think of it like that. And that comes back later on where we use a function. We just said, let's remember that this value is squared and just put in C. It makes life a little bit easier for us. So what happens when C is non-constant? So we just looked at the constant case, but let's say we have some function describing water depth. And obviously, C is going to be dependent on water depth. So then C is going to be non-constant. So you'll notice above, we have C prime sub n defined kind of as follows, but that's the asymmetric difference method. And you might wonder, well, why are we now mixing asymmetric difference with symmetric difference, and is that going to be a problem? Well, the thing is, we used a linear function to find values for C. So depending, it doesn't matter what method we use to approximate it. If we pick 2 points along that function and draw a line, no matter what method we use, we're going to get the same slope. So we just need to be aware of that, but it worked fine to use asymmetric. So if we then plug that in for C prime sub n in our approximation, you see what's on the middle line. And then through a little bit of algebra, we can just condense that, combine like terms, and you see what's on the bottom. Now, the next step would be solve for one term. So in this case, we're picking u sub n to the k. So you could say we're at a specific location, and x corresponds to n, t corresponds to k. So we're at a specific location. We know what happened at this time. We want to find what happened at the next time. So that's why we have k plus 1. And MATLAB won't understand that. So down below, we just have just a little strip of code that was applied in MATLAB to express this. And the reason we switched to A is that we defined a matrix A and basically filled in those values with the corresponding location and then a value at that location. Now, when solving for u sub n to the k plus 1, you'll notice we need a few terms. In this string, we have u sub n plus 1 to the k minus u sub n minus 1 to the k plus a couple other values. So we need to set a few initial conditions to fill that. So to better conceptualize what's happening, we get what I like to think of as kind of a plus-shaped relationship between 5 points. So this bold point you see up on the top, that would be our u sub n to the k plus 1. So hopefully you can see my cursor here. This point right here in the middle would be u sub n to the k. This right off here to the right would be u sub n plus 1 to the k, u sub n minus 1 to the k, u sub n minus 1 to the k, u sub n plus 1. Sorry, u sub n to the k plus 1 would be up here. So we need these 4 values to then build off of for our approximation. And this would be our mesh with our coordinate system, and then this point would hold the value of our wave height. So discretizing C. Now, there's some interesting things we could do here because we're looking at C as little chunks. And what's the C value here? Then what's the C value here? What's the C value here? We could theoretically use data points of water depth, from radar depth finding or whatever. But in this case, we used a continuous function with a general slope. And then from that, we found discrete values for C. So in this case, we've defined C as just being a generally sloping with a slope of 1 from a depth of 100 meters up to the shore. We played around with a lot of different equations here and got different results. So this is just one case. But something that bears mentioning is this magic constant. We have this 0.001, and this is still a bit of a standing question for me. We played with values between 0.001 and 0.0025. Anything in that interval seemed to work pretty good. Anytime we got outside of that interval, we got kind of explosive behavior on the animation of our wave. So I'm not quite sure what happened. I have a couple theories, one being maybe this is bringing us close to the C as constant. Maybe we're getting such a similar value, 1 to the next value, so similar on C that it doesn't throw things off too much. Or maybe that has to do with density and viscosity. This is something I want to look into a little bit more after this. Now then, there's also a damping force. So obviously, water waves are subjected to a lot of physical properties, and there is some sort of a damping force acting upon that wave. So we need to incorporate that. And we can incorporate that with our initial conditions and with that, with those u sub n to the k plus 1, kind of those approximating terms. So the best way to think about this, and I know this isn't what I have written up above, but it's sort of the idea A e to the negative K, which would be kind of like like what you'd use for carbon dating. The idea is we have this initial value and then it's sort of bleeding off. So that's going to kind of give us a way to build values for the decay of that wave. And then up here, gamma is just sort of associated with wavelength and so on. But we're going to say initial wave height is going to be 10 meters. We're going to plug in a value for K, and K is our damping force. In this case, these don't really bear any relevance to the physical world. They're just values we plugged in to generate a wave. But if we wanted to go in more depth, we could actually find specific values for this. And then here, we're going to initialize a whole row. So we're going to pick, let's say X is 1. We're going to pick our first X location, and then we're going to fill in all of the time steps. So we're going to say, what's the wave doing at every time at that one location? And the idea here is that, that location is essentially experiencing simple oscillatory motion. If we were to put a float on the water there, the wave's going to pass through, go up, go down, and that float is going to move with oscillatory motion. So we can fill it in as such. Then, that fills in a few of these values we need to then build our approximation, but we need a few more. So we're going to say a sub 2 comma 1, which corresponds to u sub n plus 1 to the k. We're going to fill that in as initial wave height. It's close enough to our first X location that, we can just say it's the initial wave height. And then down here with a sub 2 comma 2, which would be corresponding to u sub n plus 1 to the k plus 1, we can then just fill that in using our damped oscillatory motion model here. So what does this actually generate on a graph? So up above, we have an underdamped case. And this was generated by an earlier version of our code. As I said, we went through a few variations. So these weren't necessarily using the C values you saw before. But this was our underdamped case. And below, we have a critically damped case. Now, I want to very quickly mention a couple things about the physical properties within the wave. Now, as the wave moves into shore, it's going to meet seafloor friction, which means that water column or the wave length is going to narrow, which then forces the water up. So we're going to see a growth of that wave height as it moves into shallow water. Now, we would expect this wave to grow, but in this case, our underdamped wave did not. So we had to go revisit and change our damping force. Now here with a critically damped wave, we did see that wave growth as it moved into shallow water. However, this is not a particularly realistic wave. So I'm going to exit my slides here, and I'm going to show you a video which I couldn't open in PowerPoint. But this is the final iteration code here, and hopefully you can see that. You can see, our waves kind of going on its merry way, but here it's going to start to move into shallower water, and we're going to see that wave start to climb. And you'll notice it'll essentially have an unlimited vertical bound as it reaches the end of the graph. Obviously, this doesn't go into 0. We cut the time before it reaches that. But there it goes. You can see the water height climbing. So the last 2 points I want to make, see if I can get this back on a share. There we go. Our model does not account for the wave breaking. So in this case, our wave gets really, really tall, and that's it. In reality, that wave would ultimately break, so that's not accounted for. And then we did have those magic constants, the 0.001, and then obviously we would look for better values on our exponent k to give a realistic damping force. So this was then just our basic decaying wave when we had an underdamped wave. So I want to give huge, huge thank you to Boardman. Incredible help along the way. Whenever I got stuck, really helped me out, kept me going. And yeah, if anyone has any questions, fire away. Thank you for attending.